In 2012, I took part in an interview for Great Minds, a program produced by the Educational Broadcasting System in South Korea. It was an engaging opportunity to discuss science, rational inquiry, and the evolutionary perspective on life. What follows is a segment of that conversation. I hope you find it thought-provoking. I'm Richard Dawkins, Emeritus Professor of the Public Understanding of Science at the University of Oxford. I suppose I'm passionate about science. I'm passionate about being clear. I like to speak clearly. I like to interest people. And above all, I want to be clear. I don't want to pretend to be more profound than I really am. How could you not be interested in evolutionary biology? It's why we all exist. It's the explanation for the astounding complexity and beauty and elegance and the illusion of design which pervades all living things. Every living thing, every tree, every slug, every snail, every worm, every human, every chimp, every lion, every elephant is explained by exactly the same idea, Darwin's great idea of evolution by natural selection. My father studied botany at Oxford, and he was a naturalist. He was very good on the names of all the wildflowers, which he taught my sister and me. So I suppose I was brought up in an atmosphere of biological science. However, I myself was never much of a child naturalist. My interest was more philosophical. I was more concerned with the deep questions of existence, why we exist, what it's all about, what life is for. That was what led me, especially into my interest in biology, although my father was always in the background at the same time. Why is life so complicated? Well, I suppose it's complicated because it needs to be complicated in order to survive. What life is all about is surviving long enough to reproduce and pass on the genes that built the bodies in the first place. Even the very simplest living organisms that we know, bacteria, are very, very complicated in themselves. But of course, multicellular organisms like us and like elephants and like oak trees are even more complicated. And they're complicated because they're the end product, not the end product, but a very late product of millions of years of evolution where they have been subjected to arms races, as I call them. It's similar to human arms races between rival powers, arms races between predators and prey, between parasites and hosts, etc. And because the predators get better at it, the prey get better at it to evade the predators. And because the prey get better at it, the predators have to get better at it. Similarly with parasites and hosts. So that's part of the reason why animals are so complicated, that they need to be complicated. Predators or their prey or their parasites or their hosts. Rivals of the same species are important as well, rivals for mating with members of the opposite sex. So these are all reasons why animals are, and plants are, so complicated. Complication is one of the diagnostic features by which you can recognize a living creature. If we ever go to other planets, one of the things we'll recognize as living things is extreme complexity. The non-living world is not complex. The world of physics is not complex. Biology is the study of complexity. They're mollusks, but they're very complicated mollusks, rather highly evolved mollusks. And one of the beauties of them is that their skin changes color, not slowly like a chameleon, which is the proverbial changer of skin color, but very, very fast. So fast that it's almost as though the skin of a squid, say, or an octopus or a cuttlefish is like a television screen. It's very like a television screen, actually, because a television screen, or a computer screen nowadays, consists of millions of little pixels, where each pixel can be one of three colors. And that's just like a squid's skin. They're not quite the same three colors. They're red, yellow, and brown instead of red, blue, and green. But otherwise it's very similar. And so you could theoretically, if you rigged up the brain of a squid in some way to a computer, it hasn't been done yet, it couldn't be done yet. You could actually play movies on the skin of a squid. They almost do that. If you look at the changing color on a squid or a cuttlefish, it's like clouds moving over the surface of the sky. It's a beautiful sight. Scudding clouds moving across. They can change color in an instant. There's a beautiful picture which is in Outgrowing God of a squid, a male squid, which is showing off to a female. And it needs to be white in order to impress the female, but it needs to be darker colored, sort of brownish colored, in order to avoid being seen by predators, for example. And so right down the middle, it's split in, it has white one side and brown the other. And if it turns around, it will immediately switch colors, so it's white the other side and brown the first side. They change color instantly, almost instantly. And that's one of the beautiful things about squids and cuttlefish and octopuses. There's a lovely picture, a lovely film taken by a man called, I think, Roger Hanlon, who was swimming with scuba equipment towards what he thought was seaweed. And then suddenly the seaweed turned into an octopus and swam away. And it was an instant change. Well, this color change is fast, but all animals need color. The color of animals is very important. But the color of an animal is important for camouflage, to avoid being eaten, or to creep up on prey undiscovered, or warning coloration. Animals that are poisonous or that have poisonous stings, like wasps, are usually warningly colored. Yellow and black stripes, for example. Wasps are yellow and black stripes because they're warning predators to keep off, I'm dangerous. Then there are mimics, which look like wasps or look like dangerous animals. Hoverflies, yellow and black stripes, look like wasps. They're not dangerous, but they're fooling the predators into thinking that they are dangerous. Then color is used for sexual advertisement to attract a member of the opposite sex. Color is used for advertisements against rivals. Keep off. I can fight you. Keep off my territory. All these are reasons why animals have colors of certain types. And the only thing special about cephalopods is they can change color very rapidly. Beautiful example of a product of Darwinian natural selection. The chameleon's tongue shoots out like a harpoon to catch insects. And it's about the same length as the entire length of the chameleon itself. So it's a huge, long tongue. And it shoots out like a harpoon very, very rapidly. So the chameleon takes aim with its eyes, which are swiveled around like that, and then it takes aim at the fly, say with the insect, and then shoots the tongue out in a ballistic. And then it's fired ballistically, and then it's tethered to the animal like a harpoon, and then it sticks to the insect, and then it's hauled in, and then the insect is eaten. the first person to think of evolution. That goes back quite a long way. His grandfather, Erasmus Darwin, was one of many predecessors, and they go back further than that as well. Even natural selection, Darwin wasn't the only person to have that idea. It was independently thought of by Alfred Wallace, a younger man. Interestingly enough, both of them had the idea through having read Malthus on population. And that gave them the idea of competition, of overpopulation leading to competition. But anyway, Wallace and Darwin had the idea independently. When Wallace had the idea, Darwin and Wallace, it was arranged that papers by Darwin and Wallace should be read at the Linnean Society in London simultaneously, so that equal priority should be given to both these scientists. But nobody took any notice. That was in 1858, and nobody took any notice of that occurrence. It was sort of somehow ignored. And it was a year later that Darwin published On the Origin of Species, the book. And it had to be done at book length. Darwin himself argued it had to be done at book length in order to to get people to take it seriously. They just didn't get it until they saw it written out in book form, with all the evidence that Darwin was able to lay out. Wallace never did that. That was published in 1859 and was an immediate bestseller. And that was the thing that really influenced the world. Darwin is a great hero to me. He had, the philosopher Daniel Dennett says if he had to give a prize for the best single idea that anyone ever had, he would give it to Darwin ahead of Newton and Einstein and all the rest. It's such a simple idea. I mean, compared with what Newton did 200 years earlier, with all the sophisticated mathematics and inventing calculus in order to do it and so on, it would seem child's play what Darwin did. And yet it waited until the middle of the 19th century before anyone thought of this incredibly simple, powerful idea. There have been various theories for why it took so long. Maybe it seemed, looking at the complexity of the living world, it seemed so obvious that a simple explanation wouldn't do. But so great is the complexity of just one part of a body, like an eye. So huge is the complexity. It might have seemed almost obvious to people there can be no simple explanation. It's got to be done by a creator. And so it was an act of great courage on Darwin's part, I think, an intellectual courage to see that it could be susceptible of a simple explanation. It's an astonishingly powerful idea, almost too powerful in a way. It seems too much to believe, really, that such a simple idea could explain such an immense amount. It explains a huge amount, and yet the theory itself is extremely beautifully simple.